it's still updating the global illumination stuff in this world. It's gonna take like another like 5 minutes probably. Well, maybe not 5 minutes, but like 2 or 3 minutes. I guess it's not that bad. We can still wait it out. I guess I could get started. Actually, first, how about you guys get started? You had mentioned something about the FPGA thing, and then like wherever you are, Massler, and then I could talk about the where I am.
Sure. So, I'm in my last year here at university, and I'm in the digital VLSI concentration. So, where last quarter I was taking a class that kind of introduced like ASIC design, and we got used to the CAD software and the workflow and stuff. And then as a side project, I was like, hey, why not try putting ColorChord on an FPGA? That'd be kind of fun. And then this quarter, the next class in that series, we have to build a project of a certain complexity. And I was like, hang on, ColorChord would fit this really well. So while I initially started implementing ColorChord and Verilog for FPGAs on my stream, it now has turned into a class project that I'm working on with a partner, and we're planning on both having it on an FPGA and doing the linear visualizer with I think 50 LEDs is what my strip is, so that's what we're planning to use. Um,
Okay.
with the DFT and everything on the FPGA. But as part of the class project, I'm essentially also going to be turning it into an ASIC design in like a standard TSMC 65 nanometer process.
Cool. Are you using Genus?
No,
Oh, okay. I yeah.
not
I have
familiar with that.
played around with Genus a little bit, but yeah, that's it.
But yeah, so
Cool.
the
And
pipe dream of a ColorChord chip is suddenly becoming reality much faster than I'd ever expected.
you know what we should do? We
Hmm.
should try and get on the Google's what is it? It's not Skyworks.
Yeah, I know what you mean, the free one.
The free
Um,
Is it
130.
Sky Water?
is that it? I
Hmm?
don't remember. Yeah. I mean, while I still have access to the CAD software, I don't know how I would go about doing that, but that'd be cool. I also talked to my professor, and it turns out getting an actual chip manufactured by TSMC like this is probably going to be on the order of $35 to $40,000.
Yeah, no, chip runs are ridiculously
Ooh.
expensive.
Yeah, it's not like PCBs where you hop over to China and get yours for $2 or $5. Chips are very different.
Yeah, I have kind of my fingers crossed for this like the Skywater PDK that'll start pushing at least a few places to open up old processes because that would be amazing. But
That's
as
so.
of yet, nothing's materialized. I think if you want to do an open like the Skywater PDK, they have all the files set up so you can use the world's worst CAD software.
Oh
No,
no.
I'm not going to go that far. It's not the world's worst,
Magic?
but yeah, Magic.
Oh no.
Uh, so I just looked. Moses claims $3,000 for 40 chips.
Which process node is that?
Probably 130.
Okay.
It's
I th-
probably
Yeah,
IBM
it's gonna be
330.
something awful.
I mean, it's not that bad. Also, you have to realize ColorChord really does not need to go fast. We're dealing with audio here, and once you do it in hardware, you can optimize a lot more. So it's really not gonna be bad at all.
But you got to go fast.
But why?
The
It's audio.
I mean, you could, if you want, you can do a ColorChord one style DFT and watch like silicon go burr.
Yeah.
Like it's not bad. It's just slow comparatively.
Yeah.
So, question about ColorChord 1. That was just using the normal DFT with normal spacing, right? So, like the high frequencies had way more data than necessary, correct? That
Uh,
was
yes. Oh no, 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 no. ColorChord one is actually the opposite. So ColorChord 1 was where I started by saying I don't want FFT bins because they don't give you the right information for doing chromatic analysis. They give you like technically correct information, but they don't give you kind of ideal feedback and response, because so you end up having the same slow response in all of your high bins as you do your low bins, but that's not what you want. You want faster response in the high frequencies and slower response in the low frequencies.
Hmm.
And so that's when I realized that. So I originally, ColorChord started actually by trying to take an FFT and then turn into a pretzel to make it work. And that was like, it just turned out to be a bad idea. And like I've revisited it, and every time it ends up being a bad idea. Um, uh, the the sort of CC1 DFT, its idea was starting right now. I'm going to look at every sample of audio that I have in my past, and I'm going to make it so that, and I'm going to convolve that with a sine and a cosine function. So what I'm going to do is I'm going to get the amplitude and a phase of what is this frequency bin, like where is this frequency bin right now, both its amplitude and its phase. And higher frequencies taper off faster. So it means that it, like, I look, so for something like 440 hertz, if it's already like 20 milliseconds in the past, I couldn't care less about it. It's just garbage. It doesn't matter anymore. Forget it. But if it's something that I'm looking at that's, say, like 60 hertz, well, then I'm going to have to look back like, maybe 70, 80 milliseconds in order to like make that good. And also with ColorChord 1, the bin spacings were selected so that it was like in the chromatic scale, which just makes everything else easier. The problem with ColorChord 1 is that it means for every single frame, you have to do basically a multiply and add with a sine and a cosine for every single bin for every single piece of history. So it ends up being this computationally moronic thing to do unless you're on a GPU.
That's like, because normal FFTs n squared.
Or n log n.
Yeah. Yeah, normal DFT. Because FFT is n log n. So that would be like what, n cubed?
Yeah, squared. I mean, it depends on what kind of complexity you're actually talking about. So if you're talking about every single new sample, effectively, yes, it's n cubed. N, that's n squared. If you talk about like over time, it becomes n cubed. Which sounds horrifying, but like a GeForce 540M could just eat that up for breakfast and poop it out for lunch. Like it's not like it's that hard to do. It's just that back in the day when it was like, and back in the day of like the Celeron Pentium and stuff like that, which is when I did it, CPUs just weren't that fast. They just could not quite cut it. So
yeah,
it sounds scary, but it's actually not that scary. It's just really inefficient.
It would probably burn up my GPU on my integrated graphics card.
No, they would have no problem at all.
Oh, okay.
Modern integrated graphics cards are significantly faster than what I was working with back then.
How modern is modern? My computer.
Intel integrated graphics from 6 years ago would have no problem with it.
Okay. Wow. I love silicon.
So ColorChord, the old way of doing it really isn't that bad at all. Like it does just work. I did actually rebake all of that, but I'm going to go switch to the other thing. Okay, so with ColorChord VRC, so let me just let's back up a second. So number one is the highest possible quality is actually basically the ColorChord 1 style of doing the DFT really slowly, because it appropriately weights every single sample. It doesn't take any shortcuts, basically. And that produces a marginally higher quality. Now, the other benefit of that is if you're running on a GPU, it really doesn't matter. So like I'm going to just play this real quick, and then you guys can kind of see what's going on. So this is ColorChord VRC, which uses the ColorChord 1 style DFT. And you can see at the bottom, it has the complete, it's the sort of like, I don't know if you guys can see the colorful rainbow repeating line, but that's what's sort of the output from the DFT first stage. And I don't know how to really explain beyond that. So like, it's the output from the stage 1, which is just the pure DFT. And you'll also notice that this is neither folded nor is it fuzzed. But that's because you don't need to fuzz if you're using like a traditional like pure DFT where you take every single sample, every single frame going back. One of the other kind of bizarre restrictions that's placed on ColorChord VRC
Real quick,
is,
what do you mean by fuzzed?
The ColorChord 2 algorithm, what it does is it blurs the bins because there is inconsistency from one bin to the next of how a frequency at exactly that bin frequency will actually result in a slightly different amplitude than a frequency. Like if you go one bin over and create a tone at exactly that frequency, the amplitude would actually be different seen by each bin because of an artifact of the DFT algorithm, the Wills algorithm.
Gotcha. Okay.
And so that's a sad thing about ColorChord 2. So you need to fuzz it. But if you're doing this haha go burr FFT, it doesn't really need to do that. So one of the annoyances with ColorChord VRC is you are extremely limited in VRChat with how you can get audio. And number one is you can't get it from people's audio, which is annoying, but you can get it from audio sources. So like worlds where you have like a video player or something like that. The second one is you can basically only get every single frame up to the last in roughly 1024 samples at any given time. There's no way to get more than that. You can't find out when the time is. You can't like get a callback when new audio data comes. You can't do any of that. You just get a snapshot of now going back. This is annoying because it means you can't maintain phase information from one frame to the next. Whereas if you could actually get a higher quality signal out. So let's take a look at, where's ColorChord step 1? Oh, there it is. ColorChord step 1. So ColorChord step 1 does what I described ColorChord 1 does, in that inside of the fragment shader. So this is executed once for every single pixel inside of the stage 1 map. The stage 1 map is 48 by 8 pixels, so it's 48 bins wide by 8 octaves deep. And for each one of those, what I do is I figure out, I just do some setup, but what actually happens is for index is 0 to sample history, so for every single thing in the sample history, read out that audio frame, so it goes from the most recent to the least recent, and then multiply the current frame times a nominal sine value and a nominal cosine value for a given frequency, and taper it off with a decay. So every single sample that you go back in time, it matters less and less. So like if you have an audio, like a wave coming in, we care much more about the recent frames than we do the older frames. So this part of the sound is going to be weighted more heavily, and it makes it feel snappier. And then the last thing stage 1 does is it takes its current, like that convolved value, and then it averages it with the last frame sum. And so that's using an IIR, where you're basically saying, I want to take some of this frame and some of last frame and mix them together, and now that's my new amplitude. And then that's how this is created. So that's kind of the first big thing to understand is that, like, at least right now for my current project, I'm going back to ColorChord 1 style stuff. Um, does that make sense to you guys?
Can you explain a little bit about how the phase information is useful for ColorChord? Because I was, at least with the ColorChord 2, it seems like we're kind of pretty much just throwing out all phase information.
So actually, so ColorChord 2 does something interesting. It uses the phase information. So one of the things, so I drew this, and the problem is that in ColorChord VRC, we actually we throw away the phase information right at the first level. So what this does right here, a length ample right here, what that does is it just immediately jettisons all phase information. So every single frame we're jettisoning it. That's not ideal. ColorChord 2 keeps the phase information from one frame to the next, and it throws it away later. And let me at least start by saying why you would want to keep it. And the reason is, if you have, say, this wave here, and then say there's a discontinuity or a change in its shape, or if it's changed frequency and went back, and it's now in a different phase, this thing would have no idea that the phase has changed and that it shouldn't immediately just continue adding to that same bin. Instead, it just adds to the bin naively. So it means that other bins which are nearby end up getting polluted by each other, because they're like, well, it's close to my frequency for this little snippet I can see. But if you were to look back further, you would actually see like it canceling out because it's a slightly different phase. So ColorChord 2 actually does keep the phase information for all of the frames, and the output of its stage 1 has the phase information. And then it throws it away for stage 2, because we don't care about the individual phase of any one of these frequencies inside the spectrum. And the reason behind that is the human ear doesn't hear the phase at all. Like, it can sort of hear it if it's in relative like juxtaposition with other frequencies. So like an E sound can have a different sound if one of the overtones is shifted. But primarily with ColorChord, the difference between like an E and an E, I have a hard time making these sounds with my voice, even though they may have the same amplitude of a given frequency and an overtone. You're not going to change the color of that. The color is totally dependent on the frequency. So that's why I throw away phase fairly early on in the process. Does all that make sense?
Yeah, that makes sense.
And so the only reason that phase would be useful here would be because of the restrictions that you have on how you grab audio, correct?
No. Well, sort of. So the second reason it would be useful here is because if you can, over the last few frames, contiguously integrate this. So like right now, what it is with ColorChord VRC, basically you're stuck with this window right here, and you don't know what happened over here. Like, you just don't know. There's no way to know. You can store last frame, this frame, but you don't know the time offset of the current frames that you're decoding. So there's no way to look back. But if you were to, say, have the phase information from last frame, you could continue integrating this frame, and you would get a better result. Sorry, that probably doesn't answer your question. Can you ask it a different way?
Yeah, so I was kind of thinking because of how you get audio in VRC, that's why phase information would be useful. If this was running on embedded or regular desktop, you wouldn't have the problem where you don't know the time and you don't know the offsets and there might be discontinuities. All that kind of stuff doesn't matter on other platforms. So,
well, it kind of matters because from one frame to the next, or one audio sample to the next, you need to be able to make sure that you are like, when you're comparing the sine and cosine, that you are doing so, like, making sure that the sine and the cosine are progressing along at like this nice sine wave pattern. Like, you need to maintain the phase information is what I'm trying to Like if let's test it. Let's actually test this, because that's not hard to test right now. If I were to throw away the phase information every single frame, every single audio frame, not every single like frame, but every single sample, if I were to throw it away, what it would do is it would look something like now the amplitude of this bin is actually just a single float. And I'm going to take the amplitude of that frame right there, and we're still going to divide by the total integral. So I just saved it. Let's see what happens. Okay, hold on.
Is there even such a thing? Ooh, can we switch up all the rules and imagine a utopia? Don't be so fed up with these expectations. Make me down. My friends begging me to have love.
So by throwing away the phase information, it makes it so it's just a jumbled mess. You need to maintain the phase information as long as you possibly can. So notice how this is just a jumbled mess, because here's an example. If I have two sine waves and I want to compare them and tell the difference.
Oh, are you saying that you need the phase information so that you can know if your sine waves basically are coherently, basically so you can know if they're orthogonal or not?
Well, it's the coherence is what you care about. So for instance, here, what we have is we have one sine wave, and then over the same time period, we have a different sine wave where there's one extra sample in this other sine wave than there is this one. So they're very different frequencies. If you were to convolve them with a sine, or not convolve, if you were to just straight up multiply every single sample, what you would actually get is something effectively like the average power in this area for the green, and you would get something like the average power in this area for the black. But the thing is, when you keep the phase information, what you end up having is, so like say we convolve this green sine wave with this red one. Okay, so now at every single sample, it's the green value times the red value. Green value times the red value, green value times the red value. And so this is 180 degrees out of phase. I just drew it to make the point clear, which would mean that the sine value would have a very, very strongly negative component. Like this would be effectively like -1 sine times 0 cosine. So you'd have a very, very powerful and clear signal. Even though it's out of phase, it's going to be a really strong signal. But imagine if our black wave here was the actual wave that we were convolving. Now what would happen is hold on. Yeah. So now what would happen is you would do this at every single sample, you'd multiply. But what happens here is that the sine component is going to be really strong because it's very closely matched. But then by the time you get here, the sine component's already flipped around, so it's going to start detracting. And then when you get over here, it's going back and it's adding again. So the actual mean component, so like when you're done and you're convolved this, it would basically be 0 sine plus 0 cosine, because these samples subtract out from these samples and these samples. So like it basically, by keeping the phase information, you're able to discern a slightly different frequency because it starts canceling out. Does that make more sense why you need phase information, at least at the front end?
Yes.
Okay.
At least it makes more sense to me now.
What about you, Sam?
I'm still I'm processing that a little bit. Just hold on. Sorry.
Tell you what.
I think my issue was just I had a different interpretation of what you meant with phase information, but
because I'm thinking of this as, but once you've done like the DFT or something, you can pretty much throw it away, right? Because that phase information is important in order to make sure that you have basically you know what frequencies you get. So you can't throw it away before you've done your DFT, and it could be useful for combining multiple DFTs together to make sure that they're staying lined up, right? But after you know what frequencies are in all of your samples, then it seems like you don't really need the phase information. Because the phase information is, at least how I usually think about it, is how much sine and how much cosine you have. So like, because if you have all cosine, that's 0 phase, and if you have all sine, that's like 90 degrees phase. So knowing your phase just is telling you how shifted your bin is. But is what I'm saying make any sense? Sorry. And I'm trying to like kind of bring together my like the bits of formal DFT knowledge and actual like practical use, which sometimes is a pain.
That's difficult. I think the one thing I really want to do is just drive home why keeping the phase to begin with is important.
So can you so what is to begin with? Like at what point are we out of stage 1? Is that after the DFT, or is that somewhere else in the algorithm?
Once you're done with stage 1, it's over.
But
like
stage
you do not need any more phase information after stage 1.
And stage 1 is the DFT, correct?
Yes.
Okay. Yeah. Okay. Got it.
Now, from frame to frame, if you can keep it, if you can keep phase from frame to frame and keep that knowledge, then that's awesome. But it's you need to keep phase as much as you can until you get the amplitude of all of the bins.
Okay. Yeah. That makes perfect sense. Yeah, because once you have all the frequency bins, you don't need the phase because that's just telling you how shifted that frequency bin is in time, right?
Yes.
That's kind of what I was confusing at the beginning too. I was wondering why you need phase after you have your bins, but
also I overlisted.
Let's see if he'll say anything. Say something, overlisted.
He has spoken.
What? Oh.
He has spoken before. Something overmuted.
So I'm currently. Oh, there it is. Okay. So let's make some graphs because I like graphs.
Graphs. They're basically the reason I continue using MATLAB and Python.
Oh, you can do that in C and SVG.
Oh no.
I know I can, but sometimes it's less code in MATLAB and Python. And
Ooh, beautiful.
I don't know if I believe you. Anyway, so what we have here is we have the output signal, which is this blue thing. And you can see that it starts by being in phase with the orange and yellow ones, but then it drifts out of phase over time. And then, yeah. And so what we end up having is you have this discerned sine and discerned cosine. So if they're exactly the same frequency, so if we emit 110 and we're looking for 110, then if you look, the discerned cosine, that actually cancels out. So on average, that the cosine term goes away. But the sine term oscillates between not very correlated and extremely correlated. And so what you end up getting is sort of the sine terms average is around here and the cosine terms average is around here. And so that has a very strong amplitude. So if we're discerning 110 hertz and we're emitting 110 hertz, our actual, like, the strength of our signal is 31. But if we shift up even a little bit, like 111, then you'll start to see that starts dropping back.
Okay, sorry,
Like
I missed like the last minute. My computer crashed.
Oh no!
Oof.
So I'm on my phone right now. I will be restarting momentarily. So
Okay. So I was mostly just setting up the table, but just the idea of, did you at least hear my thing about, like, when you have really correlated signals, how like the cosine term or sine or whichever term basically cancels out, but the other term will average to be something strong.
No, I did not hear that. It crashed on me when we were discussing Python and MATLAB. Just as a time frame of reference.
Okay, so what I'm going to do is I'm actually going to add a little bit of phase offset to make it even clearer. Okay, so the idea is that I have this blue signal, which is the one that I'm emitting right now, and I'm like watching.
Mm-hmm.
And I have the yellow and orange signals, which are the ones that I'm checking that against. And so every single frame, what I'm doing is I'm taking the sine value, like this 0.5, and I'm multiplying it by the blue value, which is like negative 0.5. And then I get a new value from that for the discern sine. So in that case, it's like negative a small value. And if they're exactly in line, then what you'll end up finding is the average value of the sine and the cosine throughout that whole thing will actually be pretty powerful. So in this case, if we have the same signal going in and out, if you take that the average of the sine and the average of the cosine, not average, the sum of all of the samples in sine and the sum of all the samples in cosine, and you take the magnitude of it, you get 32. So these are like 32 international software units. It's meaningless. Don't worry about the unit. But if we say shift out of phase, so like 120 or 130, now all of a sudden what you'll see is over a history window, the discern sine value starts by being mostly positive, and then mostly negative, and then mostly positive, and then some negative, and the discerned cosine value shifts around too. Then you know that this basically cancels out, so that you can discern and say, like, I know that I'm not listening to 130 a hertz wave, but yeah, you need some history with that, and with that history, you need to be able to maintain phase through that part of the history. I don't know. I think that that's a valuable thing to at least clear up and get clear.
Yeah, I think I see where you're going at. Those and the signal that you're listening to is of a different frequency than your test sine and cosine, right? Or are they the same?
Yes. Yes.
Okay.
And the only reason you can observe that difference is because the phase keeps changing. So the relative phase between these two. So if you have two different signals, effectively what it is you could pretend they're the same signal, but the phase offset is then changing every single frame. And it's because that phase offset is changing that it eventually falls apart.
Because it's going to average out to zero because of, it's going to average out to zero because they have there's a beat frequency going on. And
yes.
So it's going to be a sine wave. Your average is zero.
Yes.
But over the short term, you'll get some values. So therefore you need a lot of samples in order to make that up, or you need to maintain phase going.
Yes. Yeah, one of the things you can imagine is that, imagine if they were the same frequency and that the phase offset was what was changing, that becomes your beat frequency. So the speed in which the phase offset is shifting around, that's the beat frequency. And because what your actual goal is to get a read on the average phase and amplitude of the difference between these signals, if your phase is spinning around and around, that then the average phase is going to basically be 0. Okay, I think that I really just want to move on at this point. hopefully I can.
Yeah. No,
Where
that,
is
that clears that up. Discord is okay.
Okay, so let's just save, reload. Is it not reloading? Oh, I think it is. It's just the FFT is rolling out. Okay. So that's out of the way now. The big difference I wanted to talk to specifically Mosler about was the difference in how we actually handle the next step. So ColorChord 2, what it does first is it tapers the bins. So if we were to play this, and I'll pause when we have a thing up on screen.
Back on my laptop again.
Actually, I should have waited until there was a clear signal so you could see. Okay. So one of the problems that ColorChord has to grapple with is that towards the ends of the octaves, things get really weird at the actual ends. Now, ColorChord 2 is in a really rough position because if you look at the actual wave output of ColorChord 2, it's actually pretty lumpy. And so what ColorChord 2 ends up doing is it first tapers off this bin. So if there's a peak at the root note, or like not the root, if there's a peak at like the lowest possible note, you don't know where that peak is. This peak might actually be here. It could be here. It could be here. Like you don't know where this peak is because it's below the frequencies that we're able to look at. And so ColorChord 2, what it does is it just says, forget it. I don't want to know about it. I don't want to hear about it. I don't have anything to do with it. And so what ColorChord 2 does is it sets up a window where it mutes the lowest frequencies until it gets up here. And then it does the rest of the bins. And then it does the same for the highest frequency, which, by the way, I don't actually know why ColorChord VRC seems to always have this in the highest octave. Don't really understand that artifact right yet. And then the next thing it does is it then folds all of these bins in on each other, so you get an amplitude of those bins overall. Sorry, not those bins, of the frequencies within those bins overall. And what you'll notice many times is, say here, the orange color and the orange color actually merge together effectively to give more prominence to orange when you were to merge it. Now, that's the second difference in how I'm doing things here. So there's a problem with that, with ColorChord 2, that ColorChord 2 runs into. And that's that if you have two different frequencies, but they're kind of lumpy like this, you can actually get confused effectively what frequency those are representing. They might be different frequencies, different notes that a person is playing, but because they've kind of been merged together in this way where you folded the FFT on top of itself, you lose that information. Versus ColorChord VRC, it just steps through this entire thing and it says, tell me where all of the peaks are. Just tell me where every single peak is, and then it marks off those peaks, and then it will merge them together later. So for instance, here, you have this peak, and they're both orange, and so they both appear as being this orange thing right here. Does all that make sense?
Mm-hmm. Yeah.
Okay, I guess another note to take note of is ColorChord 2. In this situation, if you look, there's a little bit of a red note here in this middle octave. And ColorChord VRC is able to actually pick up on that because it hasn't folded all of these octaves into each other. So that's just a draw of being able to, when you're operating on this entire like spectrum effectively, and then stepping along and looking for each one of the peaks. So like there's a peak there. That's the cyan one, I think. There's a peak there, which is the orange one, which is also, by the way, it sees these as separate peaks, but it does when it's going through and looking at the rest of the notes in stage 2. Let's open stage 2. Figure this out. I don't remember.
Using this to mess up the C++ people.
Say what?
Using this to mess up the C++ people.
Oh. No, not really.
Something tells me that maybe some comments in the code would probably help you find the right thing quickly, but what do I know?
Yeah, I will. Yeah, I will definitely be documenting this later. I have some phase 3 find peaks, which is actually not phase 3. It's actually more like phase 2 at this point.
Nice.
Phase 2. There's a comment. So first of all, I guess I load the data in, and then I step through every possible. Oh, that's right. Okay, so I step through every possible peak. That would be like, so the idea is like I say I'm looking for as many as 5 peaks, and so what I do is I step through all of these bins, counting from here to here, and I say, hey, has the value gone up? Like, is this the highest bin? And is this higher than the previous? And is it higher than the next? And so what that means is, for say the very first bin, which by the way, don't worry about the order of these bins. That's changed later. But on this stage, what would happen is it would step through each one of these bins from left to right, and it would say, aha, I found a peak, which means that it goes higher and then lower. And so you know you're at a peak, and it's currently the highest peak. And so then it records that. Then next, it does it again. And it says, aha, I found another peak right here. And it's this one. And the reason it doesn't see this one is because it's already marked it off as it checked. So what it does is it check best bin is 1. And what that does is it prevents you from like reading this bin every single time. And then once you have all of that, it then merges all of those peaks with the previous frame's peaks. And then basically says like, well, this note is really close to this note. So that means that you know, the frequency must have just changed a tiny bit from last frame to this frame. And then, hold on. Yeah, I must have changed just a tiny bit from last frame to this frame, and then it records it. And then one of the other things to note is that later on, where is it? I think it's not sort notes. One of these things here. I'll actually comment this soon. I promise. It'll look to see are there 2 peaks which are close in frequency space or actual space, and if it is, they merges those 2 together, and then that's what you end up getting out here. So right here we now have a picture of, there's a really strong yellow note. It's, you know, that's pretty clear, or orange note. There's a reasonably strong blue note, but we don't see it here. That's probably because it was strong in previous frames and it's just starting to like decay. Like you can see that over time the DFT decays and the notes decay.
So just out of curiosity, what's like the time constant on your like history decay?
So there are 2 different time constants. One is on the DFT, the first phase, And that's just so that you can have reasonable data to work with. And that time constant changes depending on the frequency. So that's why I don't have any good answer for what. There's not. I can't say like it's like 5 microseconds per whatever. It's just I found a constant where if I multiply last frame by this amount and this frame by this amount and then add them together, I get something that feels good. Does that make some sense?
Yeah.
I'm sorry that there's not a precise like, aha, if you do it with this function, this mathematical function, it will be all great. I found a way of doing it very, very fast in hardware, which is just an IIR, and then found a constant which worked well for me.
Okay, cool. Yeah, I was just curious if you had like especially for like the second time constant with the delay of fading off the old bins. I was wondering if that was put in as more of a like a in a real unit in seconds or something.
Nope. If you look, it's the let me see if I can find it somewhere here.
That one probably wouldn't be that hard to back solve from the constant, and knowing that you're just using a first order IIR filter, right?
Yep.
Yeah, that's pretty easy to back solve if we know the sample rate, which we should. So.
But that said, in this case, how often does this run, this shader?
Once per frame.
So theoretically, if someone's computer is slow, they're gonna get some weird output.
So far I've tried it at a variety of rates. It's actually not that bad. It does make it laggier, but that's actually kind of a good thing. If you can't get the audio processed fast enough, then it's best to also weight previous samples more. So you end up in this situation where it updates it whenever it can with whatever music is currently playing. And if you can't update it enough, it still is gonna it's just going to be less responsive. It's still going to give you the same quality.
Okay.
That's what I'm trying to.
Because it's working. If you're getting a worse frame rate, it's going to update the audio slower, so it's going to be working with the right data, right? That's why that works, right?
If you update slower, it will be updating the data slower, but it will also be running the IIR less frequently, and so it will be more filtered.
Yeah.
So it's not ideal. It means that it's not as snappy, but it does at least prevent you from being sad. So one of the other kind of interesting things I thought to look at was why is this not coming up? No. What am I doing wrong? I'm doing something wrong. How do I profile? I don't remember anymore. I don't know if it's you. Forget it. Wait, maybe? No, I care about. Darn, I was going to hopefully zoom out to be able to see more details about how long everything is taking. But the point is, all of this executes obscenely fast, so it's really not an issue. Mostly just because, oh shoot, did Unity crash on me? I think you did. Oh no, there we go. Mostly just because you're using an entire GPU effectively to render this tiny little rectangle. So 48 by 8 pixels is it's insanely how quickly you can do that. And then the stage 2, the thing that's trying to find all of these notes, this code only has to execute 16 times per frame. So it doesn't even really matter if it's written that well. Yeah.
Cool.
And then the last one, which I'd rather not get into right now, I'd rather kind of call it quits soon, is the linear and Voronoi outputs. But those are basically the same as ColorChord 2, except that they were written in such a way that and cells, because that's an important one. But they were written in such a way that they can run on the GPU, versus ColorChord 2 is written very sequentially. Okay. Well, I'm pretty much tapped right now. So if you guys have questions, or or anything, that would be appreciated. And I just want to encourage Mosseler, if he was up for exploring using this newer methodology, that I think that it would work out. I mean, I don't know, but I think that it would work better than the ColorChord 2 methodology of tapering and folding.
I could definitely see how it would work better. Yes.
Should we, like how ColorChord 2 has the multiple options for DFT? Could we put in multiple options for the NoteFinder? I'm just throwing out ideas.
Are you talking about the C version or my version?
The C version?
Okay.
As it stands, no. It would have to be, there'd have to be a bit of an architecture shift.
Okay. Because I was also thinking about, oh man, I wish I had more time and motivation, but I would like to make basically the DFT and NoteFinder part of ColorChord. I feel like that would be really good if we had like a library version of that, more or less. Kind of like how raw draw is, because right as it stands right now, it seems like ColorChord is kind of embedded into the application.
That's an interesting point. So this writing ColorChord in shaders has given me a brand new perspective on this. So like you can look, this is all of ColorChord. So this is stage 1. This is doing the DFT and everything else, which you should probably, you know, like if you were doing this on some, like in C, you would not do it this way. You would do it the will way. Yeah. This is stage 2, which is longer, but it's not like a huge computational system. It's this code here, and that's it. That's it. And then you have the output devices. So yeah. Like stage 1, do DFT. Stage 2, produce these notes. Stage 3, or linear or Voronoi, use those notes to actually choose colors.
Yeah. Because like reading through the ColorChord code, at least for like the first time I did it, there is a lot of stuff that's not actually ColorChord in the ColorChord code base, because a lot of it's just like reading the setup files and all of that. And it seems like it might be good if we could like kind of split out the actual ColorChord algorithm so more people it'd be easier to use in other projects.
That's a really, really good point. If you ever do have the motivation, then I encourage you to make ColorChord 3, which is a library, and then we go use it. And specifically, ColorChord 3 could also use this new methodology. And then we would have a better ColorChord that would also be easier to use in random projects. And like it would be even better, I think, if you could like pound include it as a header file or whatever. The new hotness.
Yeah, exactly. A random thought that I had the other day, was it would be kind of cool to set up multiple ColorChord outputs almost that worked over different octave ranges, because you could maybe see like if you're listening to instrumental music, sometimes you have like a guitar up in the like kind of the treble section, and then you have a bass guitar down in the bass, and you can sometimes watch the notes, and it would be kind of cool to watch them independently. That's just random thoughts, but yeah.
Okay. No, that I personally don't like that, but that's I guess probably more of a preference. But no, that's a really attractive idea to have ColorChord be a library like that. Well, I don't know. Do you guys have any other comments or questions from this? This is where I am now. I think this is fun. I actually may consider. I don't know. I do not have enough time to write live ColorChord. I just do not have enough time to do it. But if somebody else was up for it, you have ColorChord 2 and soon ColorChord VRChat as a reference.
Is this code up on GitHub yet, or no?
Yes. So this code is on GitHub, but there are still I do need to comment it, and I will comment it, and I do need to One of the things I actually need to do for tonight, because we have a tech rehearsal for the world that this is built off of, is I have to get this looking a lot better than this, because right now it's just all chunky and gross.
Yeah.
So yeah, I haven't ever used VRChat, so I have no reference for what it should look like. So it looks fine to me.
Trust me.
It looks good to technical people, perhaps.
Yeah, it's not like the fact that like when I'm back here, like doing this makes the lines like shudder in and out of existence. The oscilloscope looks all dirty. Like there's a lot of things that need to get fixed.
Okay.
I don't think I have anything else.
No, this was fun. Yeah, thanks for letting us pick your brain a little bit.
Okay.
Yeah, I'll play with this a bit. Maybe I can try and have the like interchangeable NoteFinder system in ColorChord.net. I don't think that would be too difficult to add for me.
Oh, if you get it written, I can port it to C.
Well, you could try.
You should. I would really recommend doing what you brought up earlier, which is rewrite it as a library. That would make it. That would make a lot of other parts. I think it would make ColorChord as a whole much more approachable to people.
Okay.
Like, pound include cc3.h or libcc3.h, and then it's like it an all-in-one header file, and now all of a sudden you have ColorChord in your project, whether it be on like a microcontroller or like a desktop app or like literally anything.
Mm-hmm.
Yeah. A web page.
Oh yeah, because that would open it up to using it in like web assembly or something.
Yeah. It absolutely would.
Okay. Yeah, that might get bumped up above my main efforts to hack a router. I'm still working on trying to get that SDR from out of the cable modem.
Oh yeah, fun.
I bought one and then I ended up getting distracted. I'm sad.
Yeah. Classic.
Yeah, I bought that model too, and then I realized they don't have a way to read off the flash ROM, so side project started of trying to port Bus Pirate to the STM32 Discovery, and that's where it kind of died.
Speaking of making things more accessible, specifically things like CNFA, I don't remember, or I don't know if you saw in the channel, but we kind of came up with the suggestion of maybe adding bindings for other languages. Would that be something you'd be interested in, Charles?
I would love it if somebody added it. I'm not particularly interested in myself, but you know what I really care about? Is if I could use Windows Sound API, Windows to play stuff.
Yep, saw that coming. I knew you were gonna say that when I brought up CNFA, so kind of walked into that.
Yeah, no, I think that CNFA, I think bindings for it really would be useful because, as far as I understand, like everybody else is basically using SDL or one of the really heavyweight things in their stuff, which is just making their stuff even more heavyweight. And so I think it's a place where CNFA could really shine.
I think the main other cross-platform audio library is Port Audio, and I've never gotten that to be able to work correctly.
Nobody has ever gotten that to work correctly. I don't know why or how people keep trying to use it. I can't express, like, professionally, having CNFA has made my job so much easier. When I need sound, I just get sound. I don't have to worry about it.